properties of eigenvalues and eigenvectors. So these properties are quite interesting. The first one says that the sum of eigenvalues is actually the trace of the matrix. Trace, if you remember, is just the sum of the diagonal elements of a matrix. And the statement is that the sum of the eigenvalues is actually the trace of the matrix. The proof is interesting. So if you think about the characteristic polynomial, well, assume that you have the eigenvalues lambda I, then the roots of the characteristic polynomial will have to be the same as the eigenvalues. So what I'm saying is that the roots of the characteristic polynomial will have to be lambda I, because lambda I are the eigenvalues. So characteristic polynomial is a polynomial on lambda. So if I have lambda minus lambda 1 times lambda minus lambda 2 times all the way up to lambda minus lambda n equal to 0, and if I were to expand the factors there, lambda minus lambda 1, etc., I would get a polynomial of the order n. What are the roots of this particular polynomial? It will be lambda I, lambda 1, lambda 2, etc. Because for any one of them, at least one of the factors will be 0, the whole polynomial will be 0. So those are the roots. So this is one way of implementing the roots. Now, what's the coefficient of lambda to the power n here? If I expand this out, that's actually very easy. How do you get lambda to the power n? You'll get 1 lambda from here, 1 lambda from here, and so on. And the nth lambda from here. All of them will come with coefficient 1. So what's the coefficient of lambda to the power n? It is just 1. But I also wrote the characteristic polynomial as a minus lambda I, the determinant. So if I think about it, I have terms like a1 minus lambda, a1, a2 minus lambda, and so on in the matrix, a minus lambda, and I have some other terms all over the place. So this is my huge matrix, and it's the determinant of that matrix that I'm looking at. If I expand it, the lambdas will come only from the diagonal, so that's the only place where you have lambdas. And if I expand that, there will be a term, because if I am expanding it along the first row, the minor is actually the determinant of this guy here, and then that determinant will have another minor that is here. So all the minors will have the leading element, which is aii minus lambda. If I multiply it out, there will be one term that basically reads a11 minus lambda, a12 minus lambda, all the way up to ann minus lambda, plus some other things after that. Okay, there will be other things after that. But from this, can you see the coefficient of lambda to the power n will be? It is plus or minus 1. To be more precise, it's going to be minus 1 to the power n, depending on how many n's you have. So if I want to say this is the left-hand side and that is my right-hand side, I want to equate them, then I have to make sure that the coefficient of lambda to the power n is the same. So I can write a minus lambda I is equal to minus 1 to the power n, and the product of all those terms there, and that will be in the shorthand notation a pi I equal to 1 to n, that is a product of lambda minus lambda I. So I can always write it that way. Now we talked about the coefficient of lambda to the power n. What's the coefficient of lambda to the power n minus 1? Lambda to the power n minus 1 in the expansion of the blue polynomial, blue factorized polynomial in the top, plus 5 times lambda plus 6. What's the coefficient of lambda here? So the expansion is quadratic, so there will be terms in lambda squared, lambda, and constant. What's the coefficient of lambda here? 11, because this is basically 5 plus 6. Well, let me take one more, lambda plus 1. In that case, what's the coefficient of lambda squared here? It's going to be 12 in this case. So similarly, the coefficient of lambda to the power n minus 1 in this case is going to be the sum of lambda i's, sum of eigenvalues. And what's the coefficient of lambda to the power n minus 1 in the red area here, the red polynomial that I have written down here? That is going to be the sum of a11, a22, a33, ann. It will be basically the sum of the matrix elements, because that's where lambda to the power n minus 1 will come. Coefficients of left hand side and right hand side, lambda to the power n will have a coefficient of minus 1 to the power n. Lambda to the power n minus 1 on the left hand side will have the trace, which is the sum of all the diagonal elements of the matrix, because a11 plus a22 plus a33, etc. On the right hand side, it will be the sum of the eigenvalues. So they have to be the same because this equality is a statement of truth, and that means each coefficient will have to match. Alright, so that is the statement. So the proof is right here, just by comparing the coefficient of lambda to the power n minus 1 on the left hand side, you get the trace. On the right hand side, you will get the sum of the eigenvalues. Now that proof or that statement has a corollary that states that for a real matrix A, the trace is always real because all elements are real. That means if you have complex eigenvalues, they have to appear in complex conjugate pairs so that the imaginary part will cancel off. That is one property, quite important and quite interesting. The second property is actually interesting also, but easier to prove. The product of the eigenvalues that I've written down here, and that is the determinant of the matrix. And again, that goes back to the same statement here. A, the characteristic polynomial on the left hand side is A minus lambda I, the determinant. On the right hand side, I'm just expanding it in terms of the roots. And this is again a statement of truth, should hold for all values of lambda because it's an equation. And in particular, I can put lambda equal to 0. And on the left hand side, I'll get a determinant of A. On the right hand side, minus 1 to the power n and a product of n entities minus lambda I. So there's minus 1 to the power n coming up again. So that will cancel off to 1. So that is just a product of the eigenvalues. But this also has a corollary which states that if you have a singular matrix, we know that the determinant has to be 0. That means at least one of the eigenvalues will have to be 0. So the eigenvalues will tell you something about the structure of the matrix, the arithmetic structure of the matrix, the trace, the determinant, the singularity, etc. Quite interesting. Another set of properties, eigenvalues of real symmetric matrices are real, and the proof is there in the textbook. So what we are saying is that it's a real matrix, square, transpose is the same as itself, so it's symmetric, and that implies that the eigenvalues are all real. The opposite, the converse of this also is true. The eigenvalues of real skew-symmetric matrices are purely imaginary, which is what we saw for the rotation matrix. So if A transpose is minus A, then lambda I will be such that its complex conjugate is minus the number. So remember, the complex conjugate for A plus BI, the complex conjugate will be just changing the sign of I, is A minus BI. And if the complex conjugate is a minus of the original number, that means it's purely imaginary. The imaginary part changes sign. There's one more set of properties. If you scale a matrix by alpha, the eigenvalues will scale by the same factor alpha. So if A has eigenvalues lambda I, the eigenvalues of alpha times A would be alpha times lambda I. This is fairly easy to prove. So what we have is A is equal to lambda S because lambda is an eigenvalue. And if I just multiply both sides by alpha, I get alpha times AS is equal to alpha times lambda times S. And then you can see that this matrix, call it B or A prime, has an eigenvector S with the eigenvalue alpha times lambda. The next one also is easy to prove. If you shift a matrix by alpha, I'll tell you what shifting means. The eigenvalues will get shifted by alpha. If you take A and add alpha times I to it, that is what we mean by shifting the matrix. Shift the diagonal elements by alpha. Then the eigenvalues of that shifted matrix will be lambda I plus alpha, where lambda I are the eigenvalues of the original matrix A. Again, easy to prove. So we have A is equal to lambda I times S for some eigenvector corresponding to lambda I. Now I just add alpha I to A and multiply by S. So I expand it out. I get AS plus alpha IS. So that is lambda IS because AS is lambda IS. And then I have alpha S because I multiplying S will give me just S. And then I can pull out S. I'll get this guy. Again, if you call the matrix A plus alpha I A prime, some other matrix, then that multiplying the same eigenvector will give me some constant times the same eigenvector. But the eigenvalues will get shifted by alpha. So these are things that might be important in developing algorithms for computing eigenvalues and eigenvectors. Now let me tell you the properties of eigenvectors. This is an interesting property. Eigenvectors corresponding to distinct eigenvalues are linearly independent. That means if you have a matrix, a square matrix A, and you have some eigenvectors, and if I have two eigenvalues lambda sub I and lambda sub j, then if lambda I sub I is not equal to lambda sub j, that means Si and Sj are going to be linearly independent. That means you won't be able to find a linear combination such that the linear combination is 0 without the coefficient being 0. This is proven in the textbook again. Now, the thing is, it actually applies not merely to real matrices, it actually applies to the complex matrices too, because the proof actually involves complex fields. Another thing that we mentioned earlier, real symmetric matrices have full set of orthogonal eigenvectors, and that means if A transpose is equal to A for a real symmetric matrix, then the eigenvectors are orthogonal to each other. Again, proven in the textbook. The eigenvectors of a shifted matrix, A plus alpha I, are the same as those of A. So we proved this. A plus alpha I times S is going to be equal to lambda plus alpha times S. So eigenvalues get shifted by the same factor, alpha, but the eigenvectors are the same. Now, the last one, that is actually about eigenvalues. I put it as the last one because this one I don't have a proof for. So for a real symmetric matrix again, the number of positive eigenvalues is the same as the number of positive pivots. So if you do Gaussian elimination without any scaling, with scale of course you can change the sign of the pivots. Without any scaling, if you just do Gaussian elimination, then the number of positive pivots will be the same as number of positive eigenvalues. The number of negative pivots will be the number of negative eigenvalues. Combine that with the fact that you can shift the eigenvalues, then what you can do is to take a matrix, find the number of positive and negative pivots, and then shift it by a little bit, and then see the number of positive pivots and negative pivots again. And that way you can zero in on the eigenvalues, because the moment the number changes, then you know that you have crossed the value of one eigenvalue in terms of alpha. And that can be used as the basis of an algorithm to compute the eigenvalues. This is not a very good algorithm. This is not the way it is implemented. There are better algorithms now. So this property, connecting the sign of the pivots to the sign of the eigenvalues, is called Sylvester's law of inertia. This got something to do with mechanical engineering or physics or something.